Hi everyone, so this is the practice exam 12-week midterm from fall of academic year 2018. You'll see on the front here that there are two problems, one on privileges and permissions, one on real buffer overflows that are no longer on this part of the 12-week exam. Keep in mind that that will be replaced probably by another question that you haven't seen before because we're going to have to add something that is not those two topics. So let's get started with question number 1. The first question is true or false. All addresses in this network diagram are private IP addresses. So to answer that, we need to look at the addendum to the exam, and there's a private IP address range that is 10.something, 172.16.something, 192.168.something something. So we want to make sure there are some addresses that aren't within those ranges. It's pretty easy to see from the diagram that there are a lot of addresses that don't fall in those range. 2.0.2.0 is definitely not starting with 10, 172, or 192. So this is false. All of the addresses in the diagram are not private IP addresses. What is the first assignable address in Ward Hall in dotted decimal notation? So here we're looking to see where is Ward Hall. Ward Hall is the network ID 1.1.0.0. So the first assignable address in that range is just going to be 1.1.0.1. Okay, this is just as simple as looking at the network ID and adding 1 to it because the network ID is 1 less than the lowest assignable address. Okay, next up, what is the last IP address assignable to hosts in Hopper Hall in dotted decimal notation? So Hopper Hall's network ID is here. It is 2.0.2.0. And our mask is in the form /23. So that mask is going to be 23 ones. So that's 8. 1, 2, 3, 4, 5, 6, 7, 8. That gets us to 16. 1, 2, 3, 4, 5, 6, 7 gets us to 23. So that's the beginning of the mask. And then by the definition of a mask, it's 23 ones followed by zeros. Okay, so this is the mask that we applied to any address to get this network ID. So all of these zeros can be assigned to ones in order to find the broadcast address, and the address we're looking for is actually 1 less than the broadcast address. So if we just assign this last one to a 0 instead of a 1, that'll give us the maximum address that we can have. So we are still going to have 2.0, but then 2 might change because we're changing this by setting this to a 1 and setting these to 11111110. So that's going to be the maximum address that we can have that is not the broadcast address. The broadcast address would have a 1 here as well. So 2 plus what is here is just 3. We're adding another 1, so 2.0.3 is the answer to that, or the answer to that digit. And then the final digit is going to be pretty simple. It's just all ones except the 0 at the end, so that is 254, since the maximum for 8 ones is 255. Okay, so that is our address, or our last assignable address in Hopper Hall. Next up, part D. There are 4,093 midshipmen in Bancroft Hall, each with a laptop connected to the network, plus the one router, RD. So RD is also assigned a network address. So we are actually using 4,094 addresses in Bancroft Hall. You remember, if we're trying to find slash notation from how many hosts we have, we're going to use the equation 2 to the 32 minus n minus 2 is equal to the number of hosts. So our number of hosts is 4093 plus the router, so 4094. And normally we would apply, some 32 minus n to find that number, but we're given this number instead of n. So we need to basically trial and error figure out that 32 minus n is equal to 4096. You can do this with the natural log if you want, or you can reason about what number this might be. You know, 2 to the 10 is 1024, so 2 to the 11 is 2048, 2 to the 12 is 4096. And this is something you could use, you know, just spot check on your calculator to see. Otherwise, you could take the log base 2 of 4096, and that would give you 12. So now we know that 2 to the 32 minus n is equal to 2 to the 12. We can just figure out what the exponents are now. So 32 minus n is equal to 12 for these two things to be equal, right? Because we need the same thing in the exponent. So then we have negative n equals negative 20, n equals 20. Okay, so the slash n for Bancroft Hall then in this diagram is actually slash 20. So we want to make that update for the next problem, which is to construct the routing table for router C. So router C is right here. That's where we're going to be working from. So we want to find the masks in the network. That's what I'm going to put into the table first, because we want to go from highest mask in the network to lowest mask. So let's look here. Slash 20, slash 16, slash 23, slash 24, slash 27 is our largest mask. So slash 27 is what's going to go into the table there. The network ID for that is 3.1.0.64. This is just looking at the EC310 room bubble here that has the slash 27. I'll fill in the rest in a minute here. Next up is going to be slash 24 for Rickover Hall. So we'll add that in, slash 24, network ID of 5.7.1.0. And again, that's just straight from the bubble. Next up is slash 23 for Hopper Hall. So slash 23 and network ID of 2.0.2.0. Next up is going to be the slash 20 for Bancroft Hall, network ID of 4.5.0.0. And then finally, Ward Hall slash 16, network ID of 1.1.0.0. And of course, we need to have the default route, which is slash 0, and everything will match a network ID of 0.0.0.0 when applied with a mask of slash 0. Okay, so then we need to fill in the next hops and the interface. So we're going from router C. To get from router C to 3.1.0.64, we are going out of router C from Ethernet 3. So our interface for this is going to be F3. The next address that we're going to send data to is not the network ID, but the address of the next router. So router C is going to know where the MAC address, what the MAC address of router B is on this network. And it's going to find that through the use of its IP address, which router B's IP address is 2.0.2.1. And you can check to see that we're going on F3 through the network 2.0.2.0. So we need to have some address that is in that range, but it's not the address that is router C's address on that network. We're not sending data to router C, we're sending data to router B in order to get to EC310 room at 3.1.0.64. So that's the next hop there. To get to 5.7.1.0, we don't actually go through another router. We're directly connected to that network, so we can just say that there is no next hop. And here we are going from router C out of Ethernet 2. Next up, to get to 2.0.2.0, that is also directly connected. There's no router in between us and Hopper Hall. So our next hop is nothing. And that is through Ethernet 3, because that is the line that we're using to go out. There's also an alternate route. If we wanted to go through Rickover, then to Hopper, we could do that as well, but this is a shorter path, so it's likely that this is going to be faster. Next up, 4.5.0.0, that's over here in Bancroft. In this case, there is a router in between our paths, so we go out of router C through Ward Hall, through router D, and then into Bancroft. So in this case, we need to find the address that we are going through router D at. That is 1.1.1.2. So that is the address router C is sending data to on router D to have router D forward that to Bancroft Hall. So that's 1.1.1.2. And from router C, it's coming out of router C's port Ethernet 1. And this is not going out of Ethernet 2. That's the port it's going to on router D, but it's coming from router C's Ethernet 1. So when we're constructing the routing table for router C, all of the interfaces should be something from the connections coming out of router C. Next up, 1.1.1.0. That's Ward Hall. It is directly connected, so there's no next hop, and it is also coming out of Ethernet 1. And then finally, the default route, that is going through Ward Hall, but it's going through router G to get to the rest of the internet. So we do have a next hop of 1.1.1.4, and it is, again, because it's going through Ward Hall's network to get to router G, it's going out of router C through Ethernet 1. Okay, so that's the routing table that we've constructed. Next up, we're trying to figure out, suppose an IP packet with destination address 3.1.0.129 arrives at router RC. Using the routing table, what is the next hop address to properly route this packet, and what interface does it send the packet on? Show work. So in this case, we want to look at the table and see what is the likely target for this packet. So it starts 3.1.0. All of our masks are relatively long, so at least the first 2 digits are going to have to match. 5.7 doesn't, 2.0, 4.5, 1.1 doesn't match. So it's either going to be this route or the route at the bottom, the default route. So we want to check to see, does a mask of /27 applied to 3.1.0.129, does a mask of /27 give us the same network address as we expected here? Okay, so we're going to apply that mask. That means that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, and then zeros. Okay, so that's our mask. That's just coming from, I made an extra one there. That's coming from the /27 that we see in the routing table there for 3.1.0.64. We can see here that 3 is not going to change, 1 is not going to change, 0 is not going to change, so 3.1.0 will stay the same, so we're close. 129, however, is going to be 128, and then an additional 1. And so we end up with a result of the network ID being 128. If we AND these two together, we end up with 1 and then a bunch of zeros, and that 1 is equal to 128. So our network address does not match for the first rule in the table, which means our only other option is to go through the default route, which is 1.1.1.4. And if we look across the rest of the row, it's going to go out of Ethernet 1, which is answer A. Okay, so this is basically just apply the mask in the table that looks like it might work. And then once we have the network address from that mask applied to the IP given, we know whether or not it matches that network address that we were expecting. Okay, finally, your instructor, Lieutenant Commander Loki, intends to conduct a man-in-the-middle attack to block your access from Bancroft Hall to the EC310 website hosted on web server in the EC310 room. The web server IP address is 3.1.0.85. Design a false network that your instructor would use to accomplish this. Show work. Some abilities have been filled out for you. Use the shortest mask possible. So there are multiple answers that might work. We want to have the shortest mask that we can use. If we look at the chart here, we can see that EC310 room is the network at 3.1.0.64, and that's what they show in the table down here. 3.1.0.64 is the target. The mask for that network is 27. So we are taking advantage of the fact that the routing table is going to use a longer mask first before using the shorter mask. So our mask at least needs to be 1 larger than 27 and still contain the target address. So we want to try using a mask that is 1 longer than the existing mask of 27. So we're going to count out bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 is the current mask. We need to go one more, so we want to make it 28 long. Meaning that we want to copy all of the bits from the target IP address and then pretend that our mask is 0, so the last few bits will be zeros. So then we copy down 0000, 0011, 0000, 0001, and this is just copying from the target's IP address down to this bottom for the attacker's lie. Zeros all the way because it's 0 there. And then 0, 1, 0, 1, and these are zeros because we're applying a mask of /28 in order to be one more than the previous mask of /27. So then our answer is going to be 3 there because that didn't change, 1 here, that didn't change, 0, that didn't change. Here we have 64 plus 16, so that's going to be 80. So our answer is 3.1.0.80/28. And that will capture the IP address of 3.1.0.85 that we're trying to target, but have a longer mask than the previous one of /27. Okay, that was a long question. I'm going to move on to the next one then.